solutions to the hierarchy problem. That's the question of why the Higgs boson is not a black hole. He's well known for studying the basically quantum field theory of high temperature conditions during the Big Bang. But most importantly, especially for this talk, is he's made many, many important contributions to the theoretical study of collider physics, which is the question of how we can use particle colliders kind of in great detail to learn about the fundamental laws of nature. And that's why he's here today to tell us about the upcoming muon collider proposals. So it's a great pleasure to have him here. So please join me in giving Patrick a warm welcome. Thank you.
Okay, so thank you very much for having me. It's been
sorry. So to give an example, this came out in 1982, so 40 plus years from this first snow mass. And in that first snow mass, the idea was to study the 1 TeV mass scale, which I'll explain what that is, and to build a collider with a center mass energy of 40 TeV or so. Starting with a little older node, this was what turned into the superconductor super collider, and that actually was built. And the LHC is only approaching 14 TeV of energy right now. So we planned this 40 years ago, and we still have not reached this as humankind yet. So the plan has changed and been upgraded, but the question is which collider should we build, or any, because they cost a lot of money as well. So the first point is, what is the most basic point of collider physics? Okay? It's kind of this esoteric branch of particle physics. What are you trying to do with colliders? And if you're not in the higher energy physics land, or especially if you're a younger person who's hearing some of these concepts for the first time, at the most basic level, what colliders do is they give a scientific tool to explore the unknown at the shortest distances. Okay? We're all very familiar with the idea of telescopes going to these large distances, letting us explore the universe at very large scales. But in quantum mechanics, what we understand is that colliders are our new microscope. This is what lets us explore the shortest distances out there. But this analogy is kind of rough in the sense of big versus little. We can take this analogy a little further, because sometimes colliders are kind of doing a yes or no thing. Have you found a new particle? No, okay, that's not even anything. But at the same time, they have the same analogy with telescopes as well, okay? Telescopes, you don't just stare at one thing typically. You have the ability to observe lots of different phenomena at lots of different length scales. So for instance, this is from the JWST telescope. And as we see here, we can observe different length scales in terms of extragalactic, galactic phenomena, planetary phenomena, and here even was the image of the DART mission, asteroid impact. So we have many different things you can do with the telescope. Nobody ever thinks of a telescope as yes or no, okay? Collider physics is the exact same way. Okay? Here's an example of results from the LHC, where instead of just saying, have we found a new particle or not, here's another different examples. So this histogram here represents kind of the quantum correlations amongst top quarks in terms of color flow. This represents electroweak physics, the weak force in terms of how do we look at Z boson plus a number of extra jets. This represents so-called flavor physics, B meson, like how they decay. This represents searches for new particles at the highest energies. This is kind of the bread and butter that people are familiar with the LHC, the discovery of the Higgs boson in terms of 4 electron mass. And this here represents how you can even use the same large facility to do a different kind of physics, but this is colliding heavy ions and understanding nuclear physics as well. So one facility, one mega facility, has many different applications. The only sad part is we have histograms for collider physics. Astronomy has these wonderful pictures. So that brings me to the standard Sacchiano meme, where we realize this particle physics, we're never going to look as cool in terms of what we can show. But I really want you to understand that collider physics is just the same thing in terms of a large telescope, where we can talk about so many different things, and they give us this amazing microscope at short distances. Now, why do we want to study so many different phenomena at the shortest distances? We have the most amazing theoretical structure that describes things more precisely than humans ever have in the so-called standard model of particle physics, which is based on a number of particle excitations that come from the structure of space-time and the representations of that symmetry, and we additionally have certain symmetry groups on top of it. The point, though, is this structure is so intricate, it's so based on symmetry and certain mathematical formulations that any deviation anywhere we see will imply a revolution in our entire understanding of the universe. So that's why it's not, did we find a new particle or not? It's testing all of these different features of this amazing model that we come up with for our universe. And this is maybe a better way of viewing this. This is really what the standard model is. It's this perfectly balanced thing. And any little perturbation, the entire thing falls down, and we have a new evolutionary understanding of what our universe looks like. So again, the question is, what collider? Colliders are great facilities. We want to test our understanding of nature. What should we build? Well, an amazing thing has happened, and of course, hearing this talk from a theorist. So as a theorist, it doesn't have to put any money in the game. I don't have to build the experiments, etc. I would just like the biggest, most powerful collider you can release to test whether our theories are right. But it's a little bit more subtle than that, because as these machines have become larger and larger and more complex, it turns out there's been a bifurcation in collider physics. So this is from a review in accelerated physics by Schultzev and Zimmermann a few years ago. And what's happened is this path bifurcation is that we have two different types of colliders typically. We have hadron colliders, like using protons or protons and antiprotons to get to the highest energies. Or we build a different type of collider using positrons and electrons that we call particle fractals that allow us not to reach the highest energies, but allow us to do very precise measurements. So the field of collider physics bifurcating your choice. Do you give us the most energy or not give us the most precision? That's the way it's been for many decades now. Now, where did this bifurcation come from? Okay? It's actually really simple to understand in terms of electromagnetism and radiation. And the basic idea is, if we take a bunch of particles, we want to around the circle essentially and smash them together, okay, that's kind of version of science. The point is that the synchrotron radiation loss that you have as you're going around, you're bending these particles. It depends upon what is the mass of the particles that you're trying to use. And it also depends on how tightly you're trying to bend these particles. Okay? So what happens is, if we have two options for either using protons that are abundant all around us, or using electrons which are abundant all around us, the problem is the protons and the electrons are wildly different masses. So therefore, what happens is, since protons are much heavier than electrons, we can build them to higher and higher energy machines without suffering this synchrotron energy loss. However, electrons essentially hit a wall. You see the electron colliders that have been built so far here, and even these colliders that have never been built, these are all proposals for electron colliders,
we really have no technological way of kind of getting above this TeV scale, whereas the LHC is way up here already. Okay? The only downside to this is that protons are not fundamental particles. They're kind of these bags of strongly interacting particles called quarks and gluons. So if we really want to reach an energy scale, we don't get to use all the energy in the protons. We have to kind of go above the energy, reaching this higher scale, to reach kind of the energies that we want to probe with our microscopes. Now, why are precision factories interesting if we can't get to the highest energies? Well, this is an example of a collision from Atlas that was looking at a Higgs to tau-tau event. And because protons are essentially smashing these bags of strongly interacting things, you essentially find all of these many charged tracks and all these energy deposits. It's a very messy environment, even if you can go to higher energies. Whereas for lepton colliders, this is a proposed E plus E minus Higgs factory. You see this sort of similar event, you only see a few tracks. Okay, it's much easier to do your data analysis and measure things precisely. And this also doesn't reflect the fact that these are looking at just a particular signal. There's also backgrounds of other processes that you might want. And because protons are charged under this, they're made up of this strong force, we have lots larger backgrounds as well for protons. So if we have these two options of a proton collider with more energy or a lepton collider that gives you more precision, if you want to really decide between these two things, we need some more input. We need some more physics other than just saying we can do these two options. So one thing hopefully everybody is familiar with is about 10 years ago, the LHC discovered the Higgs boson. And since we discovered the Higgs, we could go on this path of conventional wisdom. Okay? Energy is one type of machine. We use a lepton collider for a different thing. And conventional wisdom right now from a lot of the field says what we should build is a so-called Higgs factory, an E plus E minus collider to study the Higgs in a lot of detail. However, what I want to tell you about for the rest of this talk is it turns out there's an even more compelling scale. Instead of doing this Higgs factory process here, this is already a motivated physics scale if we could build a collider that actually ever achieved that energy scale. So where does this argument for this 10 TeV scale I pointed out? Like in 1982, the SNOMAS document I said at the very beginning, we wanted to study the 1 TeV scale. Now I'm saying we want to study the 10 TeV scale 40 plus years later. Okay? Well, my argument would be is it comes from 3 separate places. One is new experimental data that we've taken at the LHC. The LHC continues to run. It has a 20-year future as well. Another is understanding what that theoretical data means in terms of our language of quantum field theory, which describes the shortest distances. And the third part of it, which I'm very fond of, is we've actually understood more about our theories of quantum physics and what they allow for. Okay? So there's 3 different things that point to a higher energy scale if we can reach that higher energy scale. So let me start first with lessons learned from the LHC. Okay? So if you look, you don't have to read this. It's obviously too small for anyone in this room to read this. But this is a catalog of one type of physics activity that the LHC does, which is searching for new particles. Okay? And most of these particles are particles that some theorist has proposed for some reason or whatnot. And the LHC experimentalists take this enormous data set, complicated, analyze it, and they make these snarky plots for theorists where they say, hey, we haven't found anything you thought of. Okay? And what this represents is each of these lines is a different idea or a different channel that's searched for. And this is the mass scale that they're probing. Okay? And what we basically found is that, yes, the Higgs boson was discovered at the LHC, but current data says roughly we haven't found anything else up to the TeV scale. That doesn't mean nothing can be there, but it's kind of a rough rule of thumb of where we're probing up to right now. Now, this isn't the only way that LHC experiments can probe new physics. For instance, this is a catalog of trying to understand what is the Higgs particle that was discovered and how does it couple to all the other particles of the standard model. Okay? So you might have heard that the Higgs gives a mass to all the other particles that we know of in the standard model. So that means it has a coupling that you can search for. Now, what this graph represents is these are modifications to the couplings of the Higgs to other particles. Okay? If this was all at 1, this is exactly what the standard model prediction is. Okay? But the reason why we ever do any sort of precision physics in these sorts of tests is because we want to understand what could be the cause of any deviation. Okay, it'd be very silly to just keep measuring the same thing without understanding what the implications could be. So it turns out, using the language of the normalization group in quantum field theory, we could understand where these deviations can come from. So this is an example of, here is our Higgs particle, and it could couple to two fermions in the standard model, like up quarks or electrons, things like that. And normally this would have a value that's prescribed by the standard model in terms of these kappas of 1. But perhaps there could be some new quantum interactions that effectively modified this, and the normalization group lets us quantify what sorts of energy scales we're doing. So the normalization group says, kind of zoom out from the quantum system, and then it effectively looks like the couplings that we know and love, except they're modified in some way from these quantum effects. And what we can parameterize it by just using simple quantum estimates is that these deviations are roughly the scale of electroweak symmetry breaking that we know over the scale of new physics. So these green bars represent roughly the projections for the high luminosity LHC if we haven't found any deviations. And what you see is that the scales that we're able to probe with the LHC directly were about a TeV, and they're also indirectly with our precision program at the LHC of about a TeV or so. Now, what this tells you as one possibility is that, of course, there still could be new physics found at the LHC in the next 20 years, but it also could be suggesting there appears to be some sort of mass gap, okay, between the standard model and where any deeper explanations for what our universe come about. So this mass gap says we need to be able to probe significantly above the 10 TeV scale. Now, of course, I can say 10 TeV is bigger than 1 TeV. That's an interesting number, but it also turns out to be interesting for physics targets. Now, if the lesson from the LHC is the Higgs plus nothing else so far, then of course you could also say, well, if I don't really know 10 TeV is the right scale, maybe I just really need to study the Higgs better. Okay? That's why this conventional wisdom I said earlier says we need to just make a Higgs factory and find the properties of the Higgs better. Well, my answer to this would be no. And the reason is the following. Higgs factories, although they are a great proposal, we have the technology to build them now. I hope a Higgs factory goes forward somewhere in the world. Secretly, it's a really weird name for what the collider facility is. It turns out Higgs factories don't make enough Higgs, and they don't make multiple Higgs particles. Okay? And why does that matter for our understanding of the universe? The Higgs boson kind of gets a bad rap sometimes. It's like, hey, this was the last ingredient of the standard model. We completed the standard model. We're done. Okay? But it turns out the Higgs is the most unprecedented and unique particle in the entire universe that we've ever found. So to give an analogy here, so there was a high energy factory built for Z bosons, okay, at CERN many decades ago. It was called LEP. And that factory produced about 17 million Z bosons. Okay? And then the way you study it is these particles they're not long-lived, they just instantly decay effectively, and they decay into other particles in the standard model. But Z bosons are something called a gauge boson. They're like a photon, and all the particles that the Z boson decays to, they all have roughly order 1 branching fractions, like how many times do I go this way or this way. The Higgs boson is unlike anything else. The same branching fractions for a Higgs boson, if I just take charged particles, span 8 orders of magnitude. So if I only make 1 million of these particles, I'm definitely not doing precision physics on the charged particles that can decay to. And moreover, neutrinos are sitting way down here. You actually have branching fractions that are 20 orders of magnitude that span, if we want to understand why neutrinos have mass, whereas neutrinos, you decay about 10% of the time here in terms of the Z boson. So the Higgs boson is absolutely unprecedented, and we need a lot more Higgs bosons to study this and understand it. And now the problem, though, is if we want to just make more Higgs bosons using one of these Higgs factories, we'd essentially have to start using the power budget of the entire world to get up to these super high number of Higgs bosons. However, quantum mechanics tells us that we can actually, instead of just increasing the amount of particles we collide, we can quantum mechanically increase the cross-section for making them if we go to higher energy. Okay? So energy allows us to study the Higgs in more detail. And that was just for a single Higgs. If we want to talk about di-Higgs events, no di-Higgs events are produced at a first stage E plus E minus collider. Why does this matter? Well, one of the things we'd really like to understand is what is the Higgs potential experimentally? You might have seen a figure like this. This shows the phenomenon of spontaneous symmetry breaking because the minimum is not at the origin. And you see this in a particle physics course or some popular physics article. But the point is, this is just a theoretical guess of what the Higgs potential is. Experimentally, all we know is where is the location of the minimum. That's this so-called VEV, the first derivative. And what we've measured by finding the excitation around this is the second derivative. If we want to map out this potential, what we have to essentially do is look for higher derivatives, which means we need to look for Higgs self-interactions. And experimentally, we try to do this with more multi-Higgs production. So the question is, can we qualitatively demonstrate this coupling that doesn't exist for any other type of particle and understand whether the standard model is true? So here's kind of a visual way of looking at this, where this comes from a recent SNOMAS report that I was involved in. And this shows kind of this range of 1 would be the standard model value, and away from 1 would be a deviation. Now, these sorts of things show that we're not even close to order 1 measurement of it in terms of numbers. But visually, I like this a lot more. So this is kind of from Nathaniel Craig and Petrosian Byrne as an idea. So the black curve here is what we think the standard model would look like. The red curve is what we actually know experimentally about the vacuum of our universe. Effectively nothing. Now, what is the LHC? This is what the LHC does. The LHC in 20 years will make remarkable progress on this, but we still have a great deal of uncertainty about what the shape of the Higgs potential is. Now, especially at sort of the origin level here, and let's do a 3D version of this to say, at the end of the high luminosity LHC, this could be the vacuum, this could be the standard model, that could also be the vacuum. We have a great deal of uncertainty about knowing what our actual vacuum of the universe looks like. And we have to go to higher energies to do this. So even if we only cared about the standard model Higgs, we clearly need more energy to understand the standard model Higgs through precision and through understanding this thing about the Higgs potential, the vacuum we live in. So the question, of course, is how much energy and precision is needed? Can we quantify this any better other than saying we want more, as the theorists would always say? So to do this, we have to go and ask some sharper questions about the physics. What possibly could be beyond the standard model, and what does that imply about the scales of interest? Now, I personally would love to say that whenever we build a telescope or a microscope, we'd like to just explore the unknown. We'd like to know more about the universe that we live in. Of course, when you think about JWST or the LHC, these are so costly, so big. Trying to tell politicians anywhere, I just want to explore the unknown, you pretty much get the door slammed in your face, even if you had the most poetic version of them. However, we also have things that we do know about in the universe that we aren't sure about them. So the Higgs, as I already gave you an example, that can set scales. And dark matter is another interesting possibility. And there's other questions that I don't have time to in this talk. Now, of course, the unknown doesn't set a scale. And it's very hard to get a guaranteed return on that. And dark matter, you can really test so-called weakly intermassive massive particles with collider physics. But we aren't sure exactly whether it is this type of dark matter or not. So let me start with the Higgs and try to understand the scales involved and what it could imply. Now, as I said, the Higgs sometimes gets a bit of a bad rap. Okay, it turns out that it's the last ingredient of the standard model. But ironically, it's the last ingredient that actually gives us more questions than answers. Okay, the Higgs, even though it's sometimes not taught this way, really touches every single aspect of microscopic physics that we know in the universe, okay? From the stability of the universe, the thermal history of the universe, talking about CP violation and baryogenesis, why do we have matter versus antimatter, and all of these questions. So you can read this review that we wrote in SNOMAS, but I'm going to just take you through a couple of these to give you a picture for how important it is. So the zeroth order question about the Higgs is we want to understand the origin of electroweak symmetry breaking. So we have these forces in nature, and our picture of the standard model is two of these forces, the electroweak force gets spontaneously broken down to electromagnetism. Okay? Now, when I say this, you also say, like, what are you doing? We've had a 10th anniversary of the discovery of the Higgs boson. The Higgs boson starts with, you draw this potential is spontaneous symmetry breaking. Hey, that's our universe. Okay? So why am I still harping on this 10 years later that we don't understand the origin of electroweak symmetry breaking? Well, it turns out if you write down the simplest quantum field theory describing a spin zero particle that we think the Higgs looks like, it turns out that this potential that people draw is all based on taking these two terms that are the so-called symmetric gauge invariant versions of what we can write down, minus sign there. Okay? If I put a plus sign, the potential would look like this. I would have no electric symmetry breaking. We wouldn't exist. Okay? So this is kind of a deep-seated thing that kind of gets glossed over when you describe this. But at the same time, the origin of this minus sign determines our existence. And that's a little disconcerting to me. I mean, maybe not to you, but it is disconcerting to me that we write down the simplest possible thing and we just stick in a minus sign and suddenly our universe pops out. So we'd like to understand where this came from. And the fact is that particle physics essentially cribbed this from other areas of physics. When we were trying to understand superconductors, a potential was written down, not with the same symmetry properties, but to describe superconductors, a model of spontaneous symmetry breaking with a similar sort of potential called the Landau-Ginzburg model was written down. Okay? And the nice thing about having this phenomenological model of spontaneous symmetry breaking was that we can take this model, and if we couple this to electromagnetism, we can understand even different types of superconductors. Okay? So for instance, you have these two basic types of superconductors, type 1 and type 2. But of course, this was just a phenomenological model for spontaneous symmetry breaking. And we got very lucky in the theory of superconductivity that only about less than a decade after this was proposed as this kind of classification mechanism, the BCS theory of superconductivity in terms of Cooper pairs was proposed. And that was great. Ironically, type 2 superconductors took a lot longer. Okay? We just now have kind of an underlying microscopic description of superexchange for superconductors. So the idea is we'd like to hopefully find this sort of same analogy with the Higgs potential to see, is there a reason for why all of us are able to sit in this room? There are other deep questions in terms of, is this truly the first fundamental spin zero particle we've ever seen? Okay? So we have spin a half particles, spin one particles. It turns out that the theory of quantum field theory, based on our space-time symmetries, dictates there's only a very few possibilities for what spins of particles could be. And up until now, we had never actually found a fundamental spin zero particle. We have things that look like spin zero particles, pions and QCD, but as we know, when we probe pions at a higher energy scale of order of the rho mass, we actually see that there are some constituents inside a pion. So we want to understand, is the Higgs pion-like? Is there some dynamical mechanism that explains why we have electric symmetry breaking in the universe? So we need to kind of probe at shorter and shorter distances, just like we did with the pion, to see if there are constituents among them. And the remarkable thing is this is also very important about understanding what are the possible theories of quantum field theory, quantum mechanics, because we know that the theory that describes pions, quantum chromodynamics, if we just kind of put it on steroids and make it a bigger version of this at higher scales, it definitely can't describe the Higgs boson. Okay, so it really is some sort of fundamental problem that that the simplest examples don't explain, as that we need to keep searching for this deeper reason. And there are other very important questions that are intertwined with the origin of electric symmetry breaking. Ironically, the fact that we found this Higgs boson with the spin zero particle, if we take our modern understanding of renormalization group techniques of how physics changed at different scales, the Higgs boson should not be at this scale whatsoever. It should live at the shortest distance scale possible, not this kind of scale well below what the LHC is probing. An example of this is that if we really tried to understand robustly why the Higgs mass is what it is, why the scale of electric symmetry breaking it is, we need a larger theory, and a larger theory that explains why it's at this scale should also make a prediction for what this scale is. If it can control the quantum corrections, it can predict it where it is. So this is an example of right after the discovery, or even pre-discovery, of where we thought the Higgs was, because theorists always jump on hints. We knew it was about 125 GeV. And if you take kind of one of the examples of extending the space-time symmetries called supersymmetry, it predicted that the scale was roughly 10 TeV to make the quantum corrections give you 125 GeV. So we already knew 10 years ago that our leading theories predicted a higher energy scale that we had to get to. There are other reasons why the Higgs is very important. I'm not going to be able to go through them in a lot of detail, but we also talk about, we know that there is some constituents that make dark matter out there in the universe. There could be other sectors that are very weakly coupled to us. And quantum field theory tells us that the leading sort of connection between the Standard Model and a dark sector, quantum field theory says it should be the Higgs. That's the leading order Lorentz invariant gauge invariant combination. Okay? So by probing the Higgs, we can probe other sectors. And the last one I want to talk about for explaining why the Higgs is such a fundamental ingredient is it controls the origin and fate of our universe as well. So we have this picture that when we go to shorter distances, we're probing higher temperatures. We're going back towards the Big Bang. So we'd like to understand what happens when we heat up the Higgs potential. What sort of things happens in the early universe with it? And also the Higgs potential, since it controls our vacuum, it potentially controls the stability of our vacuum in the future. So the next era in the history of the universe, based on the Standard Model particle physics, says, let's take our Higgs potential and heat it up. Okay? So quantum field theory of finite temperature terms says you take this potential, heat it up, and it looks like this potential. So you go from spontaneous symmetry breaking to no spontaneous symmetry breaking. You don't have to know the details of this. This is basically like what everyone's familiar with, even if you're not a physics major. You take ice, you heat it up, it has a phase change. Okay? But it turns out we've had a number of theoretical advances over the recent years in understanding this as well. So we always thought for a long time in quantum field theory that the Higgs potential, when you heat it up, have to go this way. But only a few years ago, with a graduate student who's now starting as an assistant professor at Delaware, we realized if you heat it up, it could have the opposite behavior. It could become a deeper and deeper minimum. So in some sense, we're trying to understand this phase diagram of the universe. And even more so, if it happens to go this direction, we don't know whether it's a first order phase transition, second order crossover. So for instance, we can start at t equals 0. We can kind of just gently heat it up. Or it could turn out that as we heat it up, there's a barrier and there's some sort of first order phase transition between the origin and our vacuum. And it turns out, if you really want to understand, is there a first order electroweak phase transition in the early universe? So the next epoch dictated in the Big Bang, this requires you to measure the Higgs self-interactions to order about 1%. And this requires you to get to the 10 TeV scale. Okay? The fate of the universe is a similar thing. If you take this potential that we know and love, this quadratic with a minus sign and a quartic with a plus sign, and you ask, well, does it look that way at all scales? Well, these articles started coming out after the discovery of the Higgs boson about destroying our universe. And it comes from the fact that quantum mechanically, these couplings change based on energy scale. And so, for instance, this evolution of this quartic potential, the thing that keeps us in our vacuum, turns out that it could flip over at a high energy scale. So again, we need to measure the Higgs with multiple Higgs with better and the properties, it turns out, of the top quark better. The last one I just want to give you, because I've been harping on the Higgs, and I think it's the most important particle in the universe, but everybody loves dark matter too. Okay, we know it's out there. It turns out that we've had a great idea for dark matter for a long time. The weakly interacting massive particle, it has this so-called WIMP miracle, where if you assume dark matter is charged under the weak interactions of our universe that we know about, it just naturally predicts an abundance of dark matter that we should see. And it turns out to be roughly what we expect in terms of the universe. Now, we've been searching for WIMPs for decades as well, okay? With direct detection experiments, indirect detection experiments. It turns out we always haven't found evidence for WIMPs that have interactions with us. But ironically, there's two simplest, dumbest possibilities for what a WIMP could be, just based on symmetry, are this example of a representation of the weak force living here and living here. And what you see here is these projections for these future direct detection experiments we're not even touching the surface for what these simplest examples of the WIMP are. But because they have weak interactions, we can just produce them with colliders. The only downside is we're not going to produce them at the LHC because the prediction is they're too heavy to make at the LHC. We need a collider that needs at least pair producing 3 TeV, so 6 plus TeV, okay, which obviously is satisfied by 10. So for the simplest, dumbest possibility for dark matter, we need more energy. So I've hopefully kind of given you a generic case for why multi-TeV colliders are interesting. They can probe this fundamental understanding of the Higgs in our vacuum, and also possibilities like dark matter and other things I haven't even touched. Now the question is, how on earth do we get to this 10 TeV scale or higher? Now, from the beginning of the talk, I said there were two options. Okay, we could do more energy or more precision. So I definitely want more energy. So for a very long time, especially over the last 10 years, it was believed that there was only one realistic option to do this. Okay, this was take the LHC, which is the biggest machine humans have built, and make it even bigger. Okay, so this is a so-called future circular collider that's proposed to be built at CERN. And so here's the tiny little LHC of 27 kilometers, and here's the future circular kilometer, which it says 100 kilometers here, but now it's about 91 kilometers. But it's still gigantic. Okay, this is, I mean, thinking of a science experiment this big is, I mean, hopefully is mind-blowing to most of you. Okay, so the strategy of particle physics, which sometimes gets a bad rap, is kind of this go big or go home. You just keep building bigger and bigger things. Now, eventually, we're going to come to an issue where these things become so large that we don't have enough money, we don't have enough space, and how do we continue probing nature at the shortest distances? Okay? Luckily, we're not there, but this really is kind of an extraordinary scale. And the reason why this was proposed is it's actually proposing something that's already happened at CERN, which is CERN, the LHC is currently running, but before they ran the Large Hadron Collider, they had the so-called LEP collider, an E plus E minus collider, in the same tunnel ahead of time. So the idea of the plan of the future circular collider is to dig this order 100-kilometer tunnel, make an E plus E minus collider in it first to study the Higgs, and then go to 100 TeV to study at higher energies. And the reason you need 100 TeV is because these protons kind of are these garbage bags of quarks and gluons. You don't get to use all the energy. So if you want to make 10 TeV, you really need to go to 100 TeV with these protons. The problem is manyfold, okay? Not just money and resources, but what struck a lot of us, maybe that might be alive for 20, 30, 40, some of you in this room hopefully 50 or more years, is if you look at the timeline for this mega project, when we reach the next energy scale, this is starting in 2070, okay? So for any of you that are undergraduates here, like imagining something happening 50 years from now, this probably seems like it doesn't matter whatsoever. And for some of us a little older, we all know we're dead before this ever happens. So that's also a little disconcerting. The other part of this, though, is it's not just a personal sort of statement about whether we can do this physics in our lifetime, because we have a history of physics has evolved over many centuries, okay? We are on this multi-generational exploration of our universe. But it turns out that it's not even guaranteed that we'll be able to do this technologically, okay? This is going to have huge amounts of radiation for our detectors to deal with. Can we build the magnets to kind of tame these 100 TeV beasts of protons going around? So we know we want to get to this scale. However, if this is the only option, that's also a little bit scary in terms of, can we ever reach this scale? So this is what comes to the final part of the title. So it turns out there has been a secret other option around there. And the idea was why we only could use protons, not other particles, was the fact that we had this synchrotron energy loss that said we never can build an E plus E minus collider at very high energies. Well, nature turns out to be very strange. It's given us a gift, and it's called the muon. The muon is exactly the same as electron, except for the fact that it's roughly 200 times heavier. Okay? So you could, in principle, build a collider using muons instead of electrons, and so therefore you could get to higher energies. And since they're not composite particles like protons, you don't have to get to 100 TeV to reach 10 TeV. You just build a 10 TeV collider. Okay? So a muon collider, in principle, allows you to do something new that's never been done before. So this is a nice way of saying it also, because we have this paradigm where energy or precision, electrons or protons. However, since they're fundamental, we can also get high energy and we can do precision physics. Okay? So if we could build a muon collider, this would represent a paradigm change for particle physics. We can now build a single collider that let us do energy and precision measurements simultaneously and in a smaller footprint. To give a scale of this, since we only need to get to 10 TeV because they're fundamental particles, this is the LHC. It turns out with technology people are talking about, you could build a muon collider that's even smaller than the LHC. Okay? You have some slop in terms of how strong a magnets you want to put on this, but every single sort of ring that you see here is about LHC size or less, whereas FCC is this huge order 100-kilometer thing that we do. So you can make a much smaller collider if you could use muons. And in fact, one of the interesting possibilities is now the mega collider is in Europe in terms of CERN going between France and Switzerland. Turns out you can reach this 10 TeV scale fitting on the major particle physics laboratory in the US, Fermilab. It can fit on the site of Fermilab without having to go off of it. Now, of course, if the muon offers these great possibilities that have never been done before, you could say, well, why haven't we built it yet? Okay. In fact, the muon collider, the first inklings of this came out of the Soviet Union in the late 1960s of could you build a collider with this? Now, the hiccup that if you're not a particle physicist, you might not know why we have this major hiccup. Well, the muon is a fundamental particle, but it's heavier than the electron. So what happens is that the muon decays. Okay? Things decay to the lowest stable state. And it turns out that the muon lifetime is about a microsecond in its rest frame. So when we talk about these proton and electron colliders that we've been building for decades and decades in particle physics, it's very easy to find protons and electrons. Take any piece of material, there's some protons and electrons for you. Okay? Muons, since they're unstable, we don't just have them storing in a bottle. Okay? We see them all around. Cosmic rays are constantly giving us muons, but if we want to do a physics experiment with them, we need to manipulate these particles that only live a microsecond. So there's three main challenges if we were to have a muon collider as the future. The first is we need to produce trillions of these things to collide. Okay, this is the scale of how many particles we collide in particle colliders. So these things don't stick around. So how do you produce trillions of these and have them stick around for a bit? Okay. So the production is an issue. The second issue is even if you were able to produce trillions of muons and I sat them here, they would all disappear in a microsecond. So even though if I could produce them, how on earth do I do a physics experiment? So, and it's even more so than that, I need to turn it into a very, very collimated beam so I can smash muons together. Okay. So this is this turning it into a beam to do physics. And then last but not least, once I've turned it into a very collimated beam, I need to take it from the energies I produce it at and get it up to this order 10 TeV scale in a very short amount of time. Okay. So all of this has to happen. And what this requires turns out to be a type of collider that's going to have features we've never actually built before in a collider physics experiment. So the first example is how on earth do you create lots and lots of muons? Okay. Well, we can create lots and lots of muons by essentially using the same thing we do in any sort of particle collisions. We can smash things together and we can get some muons out. So this is the basic idea of what could possibly happen. If you had a lot of protons that are flying in and you hit a fixed target, okay, what happens is QCD is going to make lots of, for instance, pions that come out. And pions decay essentially always to the muon. And so this lets you create trillions of muons very easily by smashing a very high power beam on a target. But it's so high powered, you got to make sure you can actually have a target that withstands this sort of abuse. Then the problem is if you're doing kind of this brute force way of smashing things on a target to make all these muons want to go in every direction. Okay? They don't want to just sit here for us to make a beam out of them. They're flying all around. So you need to envelop your target with a very high field superconducting solenoid that can focus these muons. Okay? So if you can do this, this solves the first problem. Can you make a bunch of muons? Can you capture them and start sending them down towards something you can make a beam out of them? Now the problem is when you smash them together, even if you have this great superconducting solenoid with high field, it turns out that roughly we're talking about sort of a beach ball size beam of these muons that are coming out. Okay? Now this turns out to be very interesting for neutrino physicists. But in terms of particle physicists, what we essentially have to do is take this beam that's the size of a big beach ball and turn it into the size of roughly a strand of human hair. And you got a few microseconds to do this because these things are decaying naturally. Okay? Now it turns out this is the next major step forwards. This is something that we've done in terms of other types of experiments. This is something that doesn't have a solution we've demonstrated as of yet. Typically, when you have electrons and protons, you have a long time to kind of group them together, make a really thin beam, and then eventually smash them together. These things are decaying so fast quantum mechanically. It turns out our methods of making beams, we call cooling methods, they don't work on this time scale. Luckily, it turns out there's been physics that we've known about for almost a century that can do this. So the idea is basically, I'm going to take on my muons that are flying all over the place. I'm going to focus them onto some material, I call it an absorber. And what happens is sometimes the muons will scatter and ionize. Okay? And what that's represented here is take, for instance, a momentum vector. You think of this black angle. And after you scatter, it's going to become shorter. Okay? And then what you have to do is then you reaccelerate only in one direction. And so essentially what you're taking is this beam and you're kind of making the beam narrower and narrower and more focused. This is called ionization cooling. Now, the physics of this is nothing new. This comes from the beta block formula for ionization, the passage of particles through materials. This was developed in the 1930s. The tricky part is, can you put all these components together? A superconducting magnet around an absorber with an RF cavity all next to one another, and do this over and over and over till you cool it from the beach ball to the strand of human hair in a very short amount of time. And then last but not least, after you've kind of made the muons, cooled the muons, then you have to accelerate it up to high energy. Now this is a good thing, because as I accelerate them to high energy, I get to use the time dilation formula that everyone's kind of familiar with at some level. If I make things relativistic, they live longer compared to their time in the rest frame. And so you want to do this acceleration, but you want to do it quicker than we do for other kind of colliders. Okay? And so this is limited by essentially how fast we can ramp the magnets up to kind of make them zip around. And then finally, last but not least, we collide it. But at this point, that's part we already do all the time with the LHC and with other colliders. Now, remarkably, this sounds like a lot of new things that haven't actually existed. But we actually have a collider design concept that came out roughly in 2014, 2015 out of the so-called Muon Accelerator project in the US. So we had a design concept of how to put these things together. And then the question is, do we have all the components? Are these things that are able to be built in laboratories? And it turns out, for entirely different reasons, physicists are always exploring technologies in other directions. These basic components roughly exist in terms of what we need. The proton driver, smashing these protons on something. When we now have very high power multi-megawatt beams at the SNS, ESS, JParc, and Fermilab for the Dune project, okay? We now are talking about multi-megawatt beams. Targets that don't get obliterated instantly from putting a multi-megawatt beam on this target. Well, at T2K in Japan, we have a megawatt sort of target, okay? And at LBNF Dune at Fermilab, the neutrino project, this is supposed to have up to a 2.4 megawatt target. So within order one of what we want to do. This crazy capture solenoid to get that beach ball in the first place, okay? High field, high bore, large bore superconducting magnet. Well, it turns out that one of these now exists. This is the Iter main solenoid, okay? It's roughly the same field, same bore that we need. Okay? Ionization cooling, there's been a lot of advances in this. There's been the so-called mice experiment. And at the end of this thing, after you cool, you need a very strong field small bore solenoid. And this exists at the National High Field Magnetory Laboratory in Florida in the US. Okay, roughly a magnet, exactly what you'd want to use. And last but not least, you want to make sure you can bend these enough in a very small radius. And it turns out that the dipoles that are being installed for the high luminosity LHC are roughly what you would need here. So there are many hard engineering challenges, but it turns out that as we've been investigating in the US and there's similar effort in Europe, it turns out that all of these really are hard engineering challenges and R&D challenges. And there's no magic step that has to happen along the way. There's no showstopper. So this resulted in the so-called Muon Collider Forum report for SNOMAS that all the accelerator, experimental, and particle physics experts that contributed to this said that it turns out it looks like this is a doable project. And remarkably, the time scale is not 2070. The time scale, we could in principle start something as on the order of 20 years if we do the R&D investment now. So what do these colliders give you in terms of all those physics goals that I talked about before? Okay, so since most of you are not high energy physicists, I'm going to flash through these things, but just kind of give you a flavor for it. So it turns out, if you want to do Higgs precision physics, these are these modifiers, standard model couplings. These are many other colliders that are proposed. These are the numbers for the muon collider. Okay? You can really leapfrog when you go to this higher energy. Okay? It also offers, since the first time we have energy and precision in the same machine, if we measure the properties precisely, as I said before, quantum mechanically, this implies a scale that causes these deviations. We could search for the deviations and what caused them in the same machine, rather than doing a precision factory first, finding a deviation, then building a high energy machine to search for what caused the deviations. You get the 2-for-1 that we've never had in particle physics. The Higgs potential, okay? As I said, this was going to be the end of the high luminosity LHC. We do better than what we currently understand, but we have a lot of uncertainty. This is experimentally what the Higgs potential looks like after 10 TeV muon collider. Okay, basically the standard model or not. Okay? The other interesting thing for deeper questions, this precision that we get to really can tell us whether we have a first order electroweak phase transition at the electroweak scale. This is an example of the Higgs portal about talking to other sectors. Okay, I'm not going to take you through the whole thing. All I want to draw your attention to is this is kind of mass versus coupling of the particles, and these model lines are what quantum field theory tells you exists on. And what you see is a muon collider. These are different energies for a muon collider. You can really surpass 100 TeV proton collider very quickly in terms of a muon collider energy. Here's another example. What if the muon collider was a composite particle? Okay, these studies are talking about the scale of compositeness versus the coupling of that strongly interacting theory. And lots of these studies have been done for the so-called European Strategy Report a number of years ago. For SNOMAS, this was the first time people made projections for the muon collider. And it turns out they had to change the x-axis into a logarithmic scale because it's so much beyond every other possible option. Last but not least, we have the naturalness example for the Higgs. And it turns out that this 10 TeV scale that I said was important for predicting 125 GeV, if we have this enhanced space-time symmetry, it turns out a muon collider is excellent at this as well. And finally, the last one I'll flash is this idea of weakly interacting massive particles. Okay? The idea is the theory itself predicts what the mass scale is. Those were those dots I showed on the direct detection plots. And so for the simplest examples, the dots live here, okay, in terms of the mass scale, or here. Okay? And as I said, you really needed something like 6+ TeV to get there. And here's an example showing for the muon collider lines that if we get to a 10 TeV muon collider, we can test the simplest hypothesis for what dark matter could be. Okay? So clearly a 10 TeV muon collider is this amazing revolutionary machine if it can be built. We've done a lot of work over the last few years to kind of demonstrate the scale and understand where the technology is. And that's the last part that came to this abstract that I all presented you, which is supposed to be whimsical in some way. So what happened in the US is we had this planning process of SNOMAS. And then what happens is the Department of Energy says they make a panel called P5 because it's the Particle Physics Project Prioritization Panel. And they take all these ideas of the physicists in the community and say, who should get money? Okay, it's very ruthless. But what happened was kind of a bit of a surprise in terms of we all were excited about this. But P5 themselves, this is the logo for this panel, what they thought was this is so interesting and compelling, they themselves deemed this the muon shot, just like the moon shot. Okay? They don't know for sure if we can do this, but this is something that as a field we could technologically invest in. It works incredibly well with the US particle physics program, and we hopefully could have an end path that would be an unparalleled facility for the US. So this came from the New York Times. This was the headline after P5 came out. They also picked up on this muon shot. And just yesterday, I don't know who wrote this. I don't agree with the title, but this is still kind of circulating that US particle physicists want to build a muon collider. Europe should chip in. That's not the take I take of this, but it's still out there. Okay. So we have this unprecedented opportunity that's presenting to us. We have big physics questions. We couldn't realize this dream if we go forwards. And here's an example of how you would put all these things together on the Fermilab campus in a little bit more detail. So let me finish. A muon collider represents a paradigm change, right? We're not just doing an electron collider or a proton collider. It really is a new type of machine that allows us to do energy and precision at once. It gives you this unparalleled physics reach that I flashed in a number of transparencies. But the remarkable thing it does is it does this in a smaller machine, not a bigger machine, as we're always given particle physics saying we have to go bigger and bigger and bigger. And which is really exciting for people that are younger, is this is not just building the same thing at a bigger scale. It requires new technology. So for instance, for experimentalists and for accelerator physicists, this really is a playground that you can kind of get in and help build this new era. One of the things I haven't touched at all, but it turns out a muon collider also has the most synergies of particle physics with other kind of areas of physics inside of HEP and beyond. Muons, since they always decay, even if we accelerate them to 10 TeV, they are a playground for the best collimated beams of high energy neutrinos that we've ever made in human history. So there's a lot of neutrino physics that naturally is a synergy with this program, just like what's being built at Fermilab with the Dune experiment could be a front end for a muon collider. And there's even synergies with nuclear physics. Some of you might have heard of the electron-ion collider. That's the next major facility in the US that's being built to collide electrons on heavy ions. But even more interesting is the next one that a lot of people in nuclear physics would like to think about is what if you build a muon-ion collider, okay? And building beams of muons would allow you to do interesting nuclear physics there. As I said, this fits incredibly well with US plans, but there's also an international muon collider collaboration that CERN is hosting. And such a collider doesn't have to be built at Fermilab. It could be built anywhere in the world, in particular at CERN. So there's lots of hard work to be done, lots of engineering challenges, but it's an opportunity for the next generation to do something new. And I really hope that some of you at least are excited about this. So thanks.